Last unit we learned all about the rules of derivatives. In this unit we're going to use the rules of derivatives to help us sketch graphs. Let's go ahead and get started. The first thing I want to mention to you is that a continuous function assumes a maximum or minimum value on any closed interval. So, how is that? Well, if you have a closed interval, it means you have endpoints. So I'll just quickly draw a part of a function with a closed interval. Notice that this has to be its maximum and this has to be its minimum. So anytime we're talking about a closed interval, we will always have a max or a min. The second note I have is about a critical point. A critical point of a function is a point x sub 0, I'll name it, in the domain where the first derivative equals 0 or where it does not exist. Now I want to go ahead and talk about, really fast, the words critical number and critical point. So critical numbers, if you're asked to find a critical number, you only need to find the x value. If you are supposed to find the critical point, you need to find the x and the y values. So please take note of that so that you're answering questions properly. So critical number, just find the x value, but a critical point, you need to find the x and the y value. So we're going to be looking for critical points, and I have a sketch on the next slide that will hopefully describe this a little bit better. But again, it's where the first derivative is 0 or it does not exist. So in this picture here, I have lots of different crazy things going on in my graph. First of all, let me go ahead and just highlight what is the function here, since there's a lot of notations. I want to point out to you that every one of these arrows is considered a critical number or a critical point if you have the x and y values. Notice that this is a critical number because it's an endpoint, and the derivative does not exist at endpoints. Up here, this is a critical number because the derivative is equal to 0. Notice the slope of the tangent line to the curve is 0. Down here, this is a critical number because the slope is 0. The slope of the tangent line, that is 0. Up here, we know that the derivative does not exist because the derivative does not exist at cusps. Right here's another critical number because the slope of the tangent line is 0. Up here, again, we have another slope of the tangent line being 0. This ends up not being a max or a min or anything of great significance, but it's still considered a critical number. And then up here, we have another spot where the derivative does not exist, so it is considered a critical number. So hopefully this picture has shown you what critical numbers look like. Let's go ahead and continue on defining a few things that we're going to see in directions. The first one is extrema. Extrema is the maximum and the minimum values. So anytime you read the word extrema, know they're talking about maxes or mins. Relative extrema, or local, that's another word they could use, but relative is the one most common. Relative is it's not the highest or the lowest value, but it's still a critical number. So if I go back to this other picture, this was a local, right here, this is a local extreme. It's not the highest value. Up here is the highest value. Those highest values are called maximum or absolute maximum or absolute extrema. So it's the highest or the lowest extrema. So back to this picture, this is considered to be a local max. This one would be a local min. This seems to be the absolute minimum. This one would be the absolute max. This one is not a max or a min, it's just a critical number. This is another local or relative, I'll use that word this time, relative min. Remember that means the same thing. Local and relative are the same thing. And then this last one is another relative max. Remember, local and relative are the same words. Now that I've defined all of those different terms that we're going to run across, the extrema, local extrema, absolute extrema. I want to talk about the guidelines for finding those extrema in the closed interval. One thing we're always going to do is we're going to check those endpoints, because those endpoints, as I said, could be maxes or mins. So we're going to definitely check our endpoints. Then we're going to find the derivative, and we're going to determine what x's are equal to 0 or where it does not exist. All of those cases where the derivative equals 0 or does not exist are where those extrema occur. So we need to do both of those things in order to determine our extrema on the graph. What I'm going to start with is just pictures. So we're going to find the value of the derivative if it exists at each indicated extrema. So we're first going to go ahead and look at this point right here at -1, 0. We're going to determine the derivative of that. The derivative of this point, so this derivative at -1, it does not exist. And that's all we're going to state right now. It does happen to be an extrema because the derivative does not exist. This one up here, we're going to determine the derivative of -2/3 to be equal to 0. Notice how the slope of the tangent line to the curve is 0. On the next example I have here, we're going to look at 0,4 and determine what is going on with the derivative at 0,4. I can see at 0,4 this is a corner, and I know that the derivative at 0 then does not exist because derivatives do not exist at corners. So when you're asked to just find the value of the derivative, that's all it's really seeing is that you can see whether it does not exist or n equals 0. On this problem, we are asked to find or to approximate the critical numbers of the function shown in the graph. We're going to determine whether the function has a relative max, a relative min, an absolute max, an absolute min, or none of these shown. So number 8 is kind of a strange example. It is actually talking about an open interval. So we are not going to be checking the endpoints because it's an open interval. Had these been closed in dots, we would have said, oh yeah, this has a minimum here and a maximum here, and those would happen to both be absolute mins or maxes. But since we are talking about an open interval, we do not check the endpoints, nor do we say that there's a max or a min at those. So the only approximation that I can make is this one, that there is a critical number at, so there is a critical number at x equals 0. And that's because, and I'll put that, because the derivative at 0 is equal to 0. Is it a relative max or a relative min or an absolute max or an absolute min? No, it is not any of those things. It's not the highest point, it's not the lowest point. It actually is just a critical number. The function continues to increase throughout there. So there is actually none of these in this function. The second one we're going to look at is another open interval. I'm supposed to approximate the critical numbers. It looks like, again, I have another open interval, so I won't be checking the endpoints, but it looks like there is the slope right here. So the derivative at 2 is equal to 0. That would be a critical number. And right here, the slope of the tangent line of the curve is 0. So I'd say at 5 is equal to 0. So there's critical numbers at x equals 2 and 5. Now, we need to determine if those are relative max or mins. This one is none. It's nothing. However, at 5, this is considered the highest point of the function, so it is considered its absolute max. And I'll abbreviate that a little bit. On the next stage of this, we're going to actually find the critical numbers not given a graph. We could also graph this on our graphing calculator to determine those critical numbers. But what do we do when we don't have a graphing calculator? Well, remember, we're supposed to find critical numbers at endpoints or where the derivative is equal to 0 or does not exist. In this case, we're not talking about closed intervals, so we will not check endpoints. We'll do that later in a couple problems. So what I'm going to do is I'm just going to go ahead and find this first derivative. I have to use the rules I learned in the last unit, which is this is the quotient rule. So I need to do bottom times the derivative of the top minus the top times the derivative of the bottom, all over bottom squared. Now if you notice, what I did was to hopefully help me not have to write out things so many times. I did write bottom times the derivative of the top, but I put that top number out front because I knew I was going to have to distribute that through anyway. So my first derivative ends up looking like 4x squared plus 4 minus 8x squared. And I'll keep going here. I do want to simplify this. Negative 4x squared plus 4. And then on the bottom I have x squared plus 1 squared. So this is my derivative. Now I didn't just take a closer look at it. And what I'm going to ask myself is there anywhere where this derivative is going to equal 0 on the bottom? Because that means that the derivative would not exist if that was the case. So you always do need to check the bottom of the fraction to see if that is the case. This would yield the derivative not existing. But there are no values which will create 0 on the bottom, so I don't need to determine any critical points from there. The top, I now need to look at where does this derivative equal 0. This would actually yield derivatives equaling to 0. 0 on top and it gives you 0, and 0 on bottom is that does not exist. So what I'll do is I'll just take that top part, set it equal to 0, and solve. This will give me negative 4x squared. I could factor this as well, but I'll just solve for x squared. And I'll end up getting x is equal to plus or minus 1. Now, it did just ask me for the numbers, so I am going to be finished with that. Remember, critical numbers are the x values at which that occurs. The next example says locate the absolute extrema, so I'm only concerned with the absolute extrema on the function. And it is a closed interval. So I'm going to go ahead and start out by taking this derivative. So I can determine where it equals 0 or where it does not exist. Let's go ahead and take out a 3. And then let's factor that a little bit further. X minus 2x plus 2. So what does that mean? Well, it means at x equals 2 and x equals negative 2, those are critical numbers. It's where the derivative equals 0. Now, I am only talking about this particular interval, so I am going to cross out my negative 2 because it is not part of my interval. I am looking for the absolute extrema, so I need to test those values. I need to find out what is the y value, what is the height at 0. That's an endpoint. I've got to check this one for absolute max or min. What is the height at 2? Remember, I got that from the derivative being equal to 0, so it is a possible max or a possible min. And then the last one I need to check is at 4 because it is also an endpoint. Where do I get my y values? Well, I get my y values from plugging those back in to the original function. That means if I put 0 in for here and 0 in for here, I only get 0 for my height. When I plug in 2, I get 2 cubed, maybe I'll write that in red here, 2 cubed minus 12 times 2. Well, that is 8 minus 24, so that is a negative 16. And then when I plug in 4, I have 4 cubed minus 12 times 4. 4 cubed is 64 minus 48, which is a positive 16. So this happens to be my absolute minimum, and this happens to be my absolute maximum. It is because this is the lowest number, and this one is because it's the highest number. I have 3 more examples, and I'm determined to get through those here in the next video. So, in this one, locate the absolute extrema on the closed interval. So it's just like the last one we just did. I'm going to go ahead and find its derivative first, but before I find the derivative, I'll rewrite it. Please make sure that you are using proper notation when you're rewriting it. Now we're taking the derivative and denoting it as g prime of x. So I get 1/3 x to the negative 2/3. It's going to be a little bit difficult to think about, so what I'm going to do is rewrite it in terms of a fraction. And then I'm going to determine where does the derivative not exist or where is it equal to 0. Well, it's never going to equal 0 because I have a 1 on the top. But it will, the derivative does not exist. And where does it not exist at? Well, that would be at 0. So the derivative at 0 does not exist because it gives me 0 on the bottom of the fraction. So I need to determine where are those absolute extrema. I am looking at this interval, so 0 is within that interval. So I need to test the y value at -1, the y value at 0, and the y value at 1. What are those heights? Well, I will plug in -1 for my original, and I will get -1. I'll plug in 0, and I'll get 0, and I'll plug in 1 to get 1. So my absolute minimum is at -1, -1. My absolute maximum is at 1, 1. And that's just from this. This is the x value, this is the y value on us. This 0, 0 isn't anything but a critical point. The next one, in order to do this absolute value, we know absolute values make a v. So I need to know if that v, where that corner takes place, is within this interval. The best way to do this is just to strictly look at a graph. And I'm not even going to take the derivative of this function. I'm just going to look at a picture. The worst case worst, when we can't take the derivative of something, we need to just go ahead and sketch the graph of it. Well, what does this look like? I know that this value is telling me to move the graph up 3. And this minus in front of here is telling me that the v is upside down. And this one is telling me to move it 3 to the right. Using those rules from algebra, I can now determine that I have a graph that looks something like this. Now remember, we're only concerned about this closed interval. So I'll be checking the endpoints of -1, and I'll be checking the endpoints of 5 for absolute max and mins. But I also need to check this value, which is 3. When I plug in, and I can actually tell that there's a maximum right there at 3, and those other two have to be absolute minimums, but we'll go ahead and plug in those values. When you plug in -1 here, we get -1 minus 3, which would be a -4. Absolute value of 4 is 4, so 3 minus 4 is -1. When I plug in 3, 3 minus 3 is 0, 3 minus 0 is still 3, and I plug in 5, 5 minus 3 is 2, 3 minus 2 is 1. So what does this mean? Well, this one happens to be my absolute minimum. It's the smallest value. So I'll write that as -1. -1 is my absolute minimum. And then 3, 3 is my absolute maximum because it is the highest height. The 3 is the highest height. The last example of what I'm going to do is just take the derivative quickly. I may not get this finished. We can discuss this in time if I do not get it finished. So I've got bottom times derivative of the top, which would just be 1, minus top times derivative of the bottom all over bottom squared. When I go ahead and simplify this, I get t minus 2 minus t all over t minus 2 squared. Those cancel and I get -2 over t minus 2 squared. This is my derivative. The only critical number is right here at 2. So when t equals 2, there's a critical number. But look at my interval. This falls outside of my interval. Outside of interval. So I do not even have to check it. I only have to check my endpoints.